have to get in the habit of handing these out at the end of class, but rather I didn't do that. So I will begin with a word of prayer. Is it bouncing? La 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 la. Okay. Heavenly Father, we thank you for this day. Again, Lord, I thank you for the students. I just ask you to bless our time together, Lord. In your name I pray. Amen. Okay, so today is and so I won't always grade 4 problems. I might grade just 2 other times. And, if you can't make sense of what's on your paper, come talk to me after class or in office hours, whatever. I'm glad to explain. But today we are talking about spanning and linear independence, and eventually, if we're lucky, we might get to the CCP, also known as the linear correspondence, also known as the column correspondence property. Yes, the CCCP is a somewhat forgotten political system. All right, so spanning. Here's the question. Given V, when is V a linear combination of, let's say, V1, V2, V3, ... Vk. So let's give this thing a name. Let's call this S, all right? S is a subset of Rn. Well, fine, Fn. So let me restate the question. The question is, given a column vector, all right, and given a bunch of other column vectors, when is it that you can build a given column vector as a linear combination of other ones, right? When can we construct a given vector as a linear combination of another set of given vectors? Okay? Just to give you an example, if we had S equal to, let's say, 1, 2, 3, 1, 1, 1, we could say is V equal to 0, 1, 0. Can V equals 0, 1, 0 be written as linear combination of vectors in S? Okay. To give you a specific example, so what does a linear combination mean? What is a linear combination? I'll keep it real in this example. Yeah. Oh, okay. So, in other words, they're asking, can we find C1 and C2 such that C1 times 1, 2, 3 plus C2 times 1, 1, 1 equal to 0, 1, 0. This is a linear combination, all right? That's the question, is does there exist a choice of C1 and C2, right? So, all right, what does this problem look like if we just, collect things together a bit? What equations do we have? This is the same as like C1 plus C2, 2C1 plus C2, and 3C1 plus C2 equal to 0, 1, 0. Right, I'm just writing the equation again, like that. And, of course, that is interchangeable with the matrix, what? 1, 1, 2, 1, 3, 1, times the vector C1, C2 equal to 0, 1, 0. So this is a system of linear equations question, right? 3 equations, 2 unknowns. We could solve it by row reduction. Do you need row reduction to solve this? Probably not, right? I mean, I think I can solve this system directly, right? But my point is, we could look at calculating the work on the augmented coefficient matrix here, which would be 1, 2, 3, 1, 1, 1, and 0, 1, 0, right? And, I mean, fine. Row 2 minus 2, row 1, row 3 minus 3, row 1. What do we got? So then what happens next? Yeah. So I guess we could, we can divide that by 2.
But we already know what we want to know, right?
Yeah, fair enough. So Nathaniel's like, well, you don't need to keep going. You've already done enough that you can see what the equations look like here, right? I mean, we could finish the row reduction if you want. Let me just do it. I'm going to use this one. So row 1 plus row 2, row 3 plus 2, row 2. Oh, yeah, thank you, minus 2, row 2. And that does what? Uh-oh, right? So what's this say? That says that the system of equations is inconsistent, right? Thus, there does not exist C1 and C2 in the reals such that V is equal to C1 V1 plus C2 V2. Where I have just introduced labels because I'm tired of writing these vectors, I'm calling this one V1, I'm calling this one V2. Okay, so the answer to this question, my first example, the answer is no. It's not possible. All right? Now, there's something that we should, kind of stop and smell the roses for a second here. If we are looking at, well, actually, let me just get something out of the way here before I go any further. This has a name, all right? This idea of looking at all possible linear combinations of a set is called the span, all right? So definition. The span over a field f of S, all right, is equal to the sum I equals 1 to n, well, let's say k, of ci, let's say si, such that ci are in the field and si are in the set S. The sub f we sometimes omit, but I put it there when it matters. Like if whatever the sub f is, that says that we're picking coefficients from the field, right? So if I put a sub r, we're taking real linear combinations. If I put a sub c, complex linear combinations, right? There's some contexts where you'd want to look at both. Oftentimes we just omit the f and just say span, all right? Now S doesn't have to be a finite set. S could be an infinite set, but the span is still the set of finite linear combinations, all right? Another special case, if S is the empty set, we define the span to be just the set containing 0. Okay, that's a special case. So also, if S is equal to, S1, S2, sk, then without loss of generality, the span of S would just be equal to the set of like C1, S1 plus C2, S2 plus plus CK, SK, such that the C1, C2, CK are in the field, right, like that. Like that covers all possible linear combinations. So if you have a finite set, you can just always take the linear combination as many vectors as you got in the set. But if it's an infinite set, you need to allow for like a linear combination of 2 things, or 3 things, or 4 things, but you can't have infinitely many things. Unless you also agree that only finitely many of the coefficients are non-zero. Okay, anyway, this is what a span is. So my original example could be restated as what? We showed what? We showed that 0, 1, 0 is not an element of the span of the set containing 1, 2, 3 and 1, 1, 1. All right? Now I'll come back and make the comment I wanted to make. All right. So the comment I wanted to make was, we're in chapter 4 now, right? The first section in chapter 4 pretty much is just designed to make the following calculational observation, which is an important thing to keep in mind. If we take A times X, right? An m by n matrix, right? Then this is equal to, actually, if you look at it, x1 times column 1 of A, x2 times column 2 of A, and then finally xn column n of A. In other words, a matrix column multiplication is nothing more than a linear combination of the columns of the matrix where the weights are being taken as the components of X, yeah?
For the example you have, when we say that 0, 1, 0 is not in the span of those 2 vectors, we can say equivalently, right, that point in 3 dimensions is not on the line defined by those 2 points, right?
Oh, you're asking what this means geometrically?
Yeah.
Yeah, geometrically that means that, the span of 2 things is a plane. So there's some kind of plane. There's some kind of plane that goes through the origin. In that plane, you could think of there being the vector 1, 2, 3. There's also, the 1, 1, 1 vector in that plane somewhere. And so all possible linear combinations of the 1, 2, 3 vector and the 1, 1, 1 vector, that's what the span is. You're looking at all possible additions and subtractions of those 2 vectors. That fills out a plane. And what this calculation shows geometrically is that 1, 0, 1, 0, 1, 0 vector, it's not in that plane. So we could look at that geometrically, yeah, that's true. When we talk about the vector not being in the plane, we're talking about the point to which the vector points is not in the plane. If it pierces the plane, that doesn't count. So this is an unfortunate choice of, let me make this the z-axis, and this could be the y-axis, y cross z, yeah, so this would be the x-axis. We don't usually draw it that way. But with this choice of picture, then this vector right here, of course, would be the 0, 1, 0 vector. Yeah. Sure. So getting back to my comment, anytime we have a matrix times the column vector, we can look at that as a linear combination of the columns of the matrix. This is another way of looking at matrix multiplication. You guys look uncertain of what I'm saying. Here's an example. If I have 1, 1, 1, 2, 2, 2, and then 3, 4, 7 times x, y, z, what does that give me? It gives me x plus 2y plus 3z, x plus 2y plus 4z, x plus 2y plus 7z. And you can take that, you could factor the x out. You got 1, 1, 1, you got a y, and you got a 2, 2, 2, and you got a z times the vector 3, 4, 7. Of course, those are exactly column 1, column 2, and column 3 in the matrix. So this is another way of looking at matrix multiplication, which is, of course, important for the question of spanning, right? So here's the question again. Is V an element of the span of, let's say, S1, S2, dot, 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 Sk? These are all column vectors, right? Let's just think about the problem. I've showed you an example. Let's think about the problem sort of generically, right? So what does this amount to solving? This amounts to solving, is V equal to C1S1 plus C2S2, right? Plus CK SK. We can rewrite that as what, though? We can rewrite this as S1, S2, Sk times the vector of unknowns, C1, C2, Ck, right, like that. And what row reduction would we do to try to decide whether or not that system actually had a solution? We'd look at the augmented coefficient matrix of what? We would want to calculate the reduced row echelon form of S1, S2, Sk, and then at the very end, we'd slap V. And depending on the details of that row reduction, we'd find out whether or not V was in the span of S1 through Sk, just like I did in my first example. So all the questions in your homework about spanning, those are just systems of linear equations in disguise. You can already solve those problems. You just have to understand them for what they are. You already know how to solve this problem, row reduction, right? What's the answer? There are two cases, right? If this is equal to stuff, and there's a 1 in the last, how to say this? Well, I don't even want to say it again. We've said this before. Either it's a consistent system or it's an inconsistent system. When is it consistent? If the last column's not a pivot, right? It's consistent if the last column is not a pivot column, right? Because the last column being pivot column corresponds to the case we had in example 1, that it's an inconsistent system, right? Here, hypothetical example. Suppose you're given S1, S2, S3, and S4, and V such that the reduced row echelon form of S1, S2, S3, S4, and V. So in this context, I sometimes put a double bar on the last one because it's got a different meaning, right? Like, the last column is the inhomogeneous term. It has a different interpretation than the first k columns because those are the vectors from the spanning set. So suppose this worked out as follows. So where do you guys want this to be? R3, R4? You pick. R2? R3, all right, great. So suppose this works out to 1, 0, 0, 2, 0, 0, 0, 1, 0, and 0, 0, well, let's say, find 0, 0, 1. Right, and then the last, and the last one works out to, I don't know, 8, 6, 7. So my question is V an element of the span of S1, S2, S3, and S4 here? And if so, state the precise linear dependence. You're like, but you didn't even tell me what S1, S2, S3, and S4 are, and you didn't even tell me what V is. That's true, I did not, because I don't want to distract you with those details. You could do that calculation just like I put right above. Plug them in the matrix, you row reduce, great. What does this mean?
X plus 2y equals 8, or S1 plus 2 is 2.
Right, so that says that 1 times S1 plus 2 times S2 is equal to 8 what? 8V? Is that what that means? I don't know if I believe that.
Doesn't it mean that C1 plus 2C2 is equal to D?
It means that what? C1?
C1 plus 2C2 is equal to 8.
Uh-huh. And?
C3 is equal to 6.
Right.
C4 is 7.
Right. And what does this tell us about C1? This tells us C1 is equal to 8 minus 2C2. Right? So actually, I said state the precise linear dependence, but perhaps that's misleading, right? Because there's not just one possible linear dependence, there are infinitely many ways we could see the linear dependence, right? Any choice of C2 gives us a linear dependence. Let's look at C2 equal to 0, right? So setting C2 equal to 0, we have what? We have C1 equals to 8, C2 equals to 0, of course, C3 equals to 6, and C4 equals to 7. What's that mean? That means that V is equal to 8S1 plus 6S3 plus 7S4. And that is, of course, an element of the span of S1, S2, S3, S4. And it's not the only one, right? I mean, you could make C2 equal to anything you like, and it would give you a different way to build V as a linear dependent, as like a linear combination of the given vectors V1 through V4. So this is a nice way to ask a test question to see if people understand what they're doing. If I give you specific if I give you specific vectors with numbers in them, yeah, you can do the row reduction, and that will be part of the test, right? But at the end of it, you guys make mistakes, and it's impossible for me to see whether or not you understand the concept. If I ask a question like this, then it shows me whether or not you understand the big idea here. Yeah.
So when we did that, C2 would have had a value with the 4 numbers in the precise linear dependence.
Well, let me replace, let me replace the question with a greedier question. State all possible linear dependencies of V. Right? State all possible ways that V could be linearly dependent. That would be V equals to, well, 8S1. And then what is C2? Oh, excuse me. I've already messed it up. C1 was equal to what? Right, 8 minus C2 times S1 plus C2 S2 plus 6 S3 plus 7 S4 for any choice of C2 in the field that we're working over. Probably the reals, but you know. So any C2 would work here. I chose C2 equal to 0 just to make it less uncomfortable. So, I mean, there's different ways I could ask the question, right? Explicitly indicate how V is linearly dependent on the given generating set. Versus the more difficult question, explain all possible ways that V could be built as a linear combination of vectors in the generating set. What's in brown describes all possible ways that V could be built. Yeah. I keep using this word generating set. What's the generating set? In this definition, S. S is the so-called generating set. This is more exciting if you're not given the generating set from the outset, right? Let's look at an example where we're not given the generating set, but we have to find it, okay? So, oh, top hat. Oh, you made me say the word. Ah, now I feel dirty. Son of a gun. You may now get out your phones. No. You can keep your phones out. I don't care. Doesn't matter to me. Okay, example. Let's consider the plane, which is the set of points x, y, z, such that x plus 2y minus 4z equals to 0. My claim is that P is equal to the span of S. Your problem, your mission, if you choose to accept it. Find S. All right. So if XYZ is in P, then what? X plus 2y minus 4z is equal to 0. Right? I think we can solve for x. Right? X is equal to minus 2y plus 4z. Now what I'm going to do, xyz is equal to what then? Well, x is minus 2y plus 4z, right? And y is what? Y is y? Why not, right? Z is z. It's easy to see. I'm sorry. That was unanticipated and horrible. What do you expect the spanning set to, how big do you expect the generating set to be? It's a plane, right? Just to give you kind of a sense of the intuition, if this thing is two-dimensional, we kind of think maybe we need two things to build the plane, right? And I think we can see those coming out here. So I factor out a y. I've got -2, 1, 0. And I factor out a z. I've got 4, 0, 1. Right? And if we allow y and z to be anything in the reals, what is that? I mean, that's a linear combination, right? So as you allow x and y, y and z to vary, this describes the span of those two vectors. So it follows that P is the span of -2, 1, 0, 4, 0, 1. Now you guys could give me an arbitrary point in R3 and ask me, is that point on the plane? Right? Follow-up question. What if I look at, first of all, you guys, does this make sense? Okay. So here's a question. Is the point ABC, arbitrary ABC, is it in the plane? What does that amount to? What row reduction would you have to do to decide that? So then the question would be, to see if ABC is in the span of these specific vectors, -2, 1, 0, and 4, 0, 1, we need to look at the following system of equations, right? -2 1, 0, 4, 0, 1. Oh, I'm sorry, my brain just jumped. So I'm supposed to look at the reduced echelon form of what? -2, 1, 0, 4, 0, 1, and then the ABC that I'm trying to decide. Is it in there? What does that equal to, So we can do that. I'll do it down here. I think life is easier if we do what? Divide by -2 the first row. Yeah, I was going to put 1, 0b up here, and then 0, 1c there, and then -2, 4a to start with. Just do some row swaps to put things in order. With that done, then I can just do, like row 3 plus 2 row 1. Which gives me what? 0, 4, a plus, what is it? A plus 2b. And then what's my finishing blow here? How about row 3 minus 2 row 2? Yeah? 4. Oh, 4. Good grief. 1, 0b, 0, 1c, 0, 0. And what we got? A plus 2b minus 4c, yeah? So what condition do we need on a, b, and c for it to be in the span of these two vectors? Or in other words, a and b and c in the plane, if a plus 2b minus 4c is equal to 0. Is this surprising? I hope it's not surprising. What was the condition that defines the plane? Right, so we didn't really need to calculate all this, right? We could have just answered the question without this calculation, right? Right. Okay. Now, if I can find my juice. Where's, the juice. So the question then, well, there are other questions, like what if you had more than one vector and you wanted to decide whether it was in the span? What if instead of just having a v, you had like a v1, a v2, a few different v's? What would you do? What if I was trying to decide, you know, suppose I was trying to decide is v1, v2, all the way out through, let's say, vt in the span of s1, s2, all the way out through sk? Well, what I would do is simply look at the reduced row echelon form of the S1 with S2 glued all the way on out to SK, and then I would put V1, V2, VT over here, because I can solve multiple systems at once, right? And I can also solve multiple spanning questions at once by putting the generating set first, and then putting possible, you know, I don't have a good name. The thing we're trying to decide, is it or is it not in the span, right? The questionable, the vectors that we're questioning, are they in the span or not? Those vectors we put at the end. You do row reduction, and you look at each column to decide whether or not the system of equations corresponding to the spanning question is consistent. But if we can do it for one vector, we can do it for t, just the same. I have examples in the notes I will project if I have time here. Okay, so that's one thing, is we can also look at spans of more than just one. But what I'd like to spend the remaining 10 minutes of class talking about is linear independence, all right, which is the other question. So here's the question. You know, we've got some set W, which is the span of S for S, some subset of Rn, okay? Can we remove vectors from S and, you know, let's say like S minus, I don't know, a vector v, and say that's S tilde, right? So take S, take a vector out of it, and yet still get the same span. Right. So just to give you an example, right? We could look at W equal to the span of minus 2, 1, 0, 4, 0, 1, 2, 1, 1. Right? Right? you can easily prove that this is equal to the span of minus 2, 1, 0, comma 4, 0, 1. Why? What's the third vector in my first generating set? So I'm thinking of this as being S, thinking of this as being S tilde in the question posed above, all right? And so this guy is my V in terms of the brown comment above. What is V as it relates to the first two vectors? Can you see it? Yeah. Exactly. So V is nothing more than minus 2, 1, 0 plus 4, 0, 1, right? So clearly V is an element of the span of S tilde because it's built from a linear combination, right? So it then follows that the span of S tilde is a subset of the span of S, and the converse direction is also obvious. So these are equal, same set. So when this happens, that vector V is redundant, right? V is a redundant vector. And we'd like to have a definition that sort of characterizes when a given generating set has no redundancy. So it's like as small a generating set as we can get. S tilde here is an example of that, right? If I take away either one of these vectors, I'm not going to get the whole plane anymore, right? So these are what we would say, these form a linearly independent set. In contrast, S is linearly dependent because the third vector can be built as a linear combination of the first two. It turns out the most convenient way to define linear independence is as follows. Definition. S, a subset of Rn, is linearly independent if and only if whenever C1 S1 plus C2 S2 plus plus CK SK equals to 0 implies that C1 equal to 0, C2 equals to 0, CK equals to 0 for any finite collection of vectors in S. Let me put it into words. A subset of Rn is linearly independent if whenever you look at a finite linear combination of the vectors in S, if you set that linear combination equal to 0, it forces it to be the trivial combination. The trivial combination being the combination where C1 is 0, C2 is 0, all of them are 0. You could easily prove that S tilde is linearly independent. So because C1 minus 2, 1, 0 plus C2 times 4, 0, 1 equals to 0. This, I just have to look at that equation. If only the zero solution for C1 and C2 appears, that proves that S tilde is linearly independent. I don't need matrix techniques for this, right? I mean, this is what? This is minus 2 C1 plus 4 C2 equal to 0, and C1 plus 0 C2 equal to 0. Oh, therefore C1 equal to 0 from the second component. And once you know that C1 is equal to 0, that implies that 4C2 is equal to 0. So therefore C2 is equal to 0. That proves, therefore by the definition of linear independence, S tilde is linearly independent. Yeah.
Would you be able to take one of the other two vectors out of S and still have the same span?
Now that's an interesting question. What are all possible subsets of a given generating set which are linearly independent? And how do we ascertain given a set of k vectors, which possible selection of those k vectors gives us linearly independent subsets? Yeah. In this case, yeah, I think so. I mean, you're asking if I take the first and the third, is it linearly independent, right? Yeah. If I take the second and the third, is it linearly independent as a set? Yes. I happen to know this as a knee-jerk comment because for two vectors, we can prove that two vectors are linearly dependent only if one is a scalar multiple of the other. And I can just look at a pair of vectors and see whether or not they're linearly, whether they're a scalar multiple of the other. So, linear independence of a set of vectors. How do you, how do we test it? Is S1, S2, Sk linear independent subset of Rn, right? How do you, what's the calculational test for this? Well, the definition says all we have to do is set a linear combination of these equal to 0 and see, does it only permit the 0 solution? So that's C1S1. So we say suppose, and then this gives us what? This gives us S1, S2, Sk times the vector C1, C2, Ck equal to the 0 vector. We've seen this before. This is the homogeneous system, right? So we can study the reduced row echelon form of S1, S2, Sk. And if you want, you can put the 0 at the end, right? So you'd have to study that to decide whether or not only the 0 solution exists. What is it going to take for only the 0 solution to exist? What can we not have here? Is the homogeneous system consistent? It is, right? So if there's a if there's a non-pivot column, we're up a creek, because that means that there's infinitely many solutions, which violates the definition of linear independence, which says there's only the trivial combination. So if there is a non-pivot column, that means that the vectors are linearly dependent. How that happens is surprisingly clear in view of the CCP, which I'll talk about next time. There's something very beautiful and simple that we can say from row reduction and the interplay between the columns, but next time. So.